This is geometry lesson 4.1, reflecting points. So we're jumping into chapter 4 and we're going to be looking at a new transformation called a reflection. So the big idea says a reflection over a line is a transformation of the plane in which the line acts like a mirror. So we're going to reflect a pre-image over a line. It's going to flip onto the other side, and the mirror image is going to appear on the other side, equal distance from the reflecting line. So as we examine the figure below, we can see pre-image is over here, reflection image is on the right. So pre-image is the original, image is the new one, and line M, okay, the line that it flips over, is called the reflecting line or the line of reflection. Now this line is the perpendicular bisector of the segments that's connecting corresponding points. Corresponding points is E in the image of E, L in the image of L. And you'll notice they're matching, they're in the same spot on the dog, they'll be on the same spot on the shape. So this line is going to be the perpendicular bisector. Perpendicular meaning it hits at 90 degrees. We can see that marking here. And bisector means it's cutting it perfectly in half. So if I take the line that connects the dog's eye to the new eye over here on the image, okay, line M, the line of reflection, cuts that perfectly in half. That's the bisector. And that's what these markings show you. These two slashes tell you that this segment matches this segment. This one slash tells you this segment matches this segment. So the line M is cutting these segments perfectly in half, so you get two equal segments. And not only that, it's hitting at 90 degrees. And think about why that's important. So when I flip this pre-image over this line and I get the image, okay, each one of these corresponding points is going to be the same distance away from the reflecting line. So this distance here from F to the reflecting line, let's just say it's 10. These markings tell you the new corresponding one, when it flips over, it's going to be the same distance just on the other side. So it's also 10 away. But why is it important that we have this perpendicular bisector, not just the bisector? And think about it, I could make a line from here to here that's say 12 and keep it going on the other side, another 12, but that's not the corresponding point. So the corresponding point is always going to go directly to the reflection line, and it's going to hit it at 90 degrees. All right, and the definition of a reflection image is explained there, just in a little more complicated language, so that's there for you. But the key is that we understand the corresponding points are going to be the same distance on the other side, okay, and the segment that connects corresponding points is going to hit the line of reflection at 90 degrees. Now, when we show the notation for these reflections, this is what it's going to look like. Little r represents reflections. If you remember back to rotations, we used a capital R. Right? We didn't spend a lot of time focusing on them, but we did use a capital R for rotations. So lowercase r is for reflections. And so this statement here would be read, the reflection image of A is the image of A. Now, this is the way you write it. If there's really no controversy over what line we're reflecting it over. Because if you notice, this just tells you we reflected something, a shape, a point, something, and we get a new one on the other side. But this doesn't tell you anything about the line that we reflected it over. So if we want to emphasize the reflecting line, we would write it like this. So the reflection over the line M, so this is the line. This represents your pre-image. And then this is your image. Now notice they use different letters. You don't have to. This could be Q with the little marking. But it's important to see this is the line that we're reflecting it over. So this statement is read, the reflection image of Q over line M is P. Or R of Q over line M equals P. But that's just more shorthand. We want to use the word reflection so we know what we're talking about. So let's try and make sense of that here, down to the bottom. If you look at this picture, I've got two lines, and I've got these points that were reflected over one of those lines. Okay, so A was reflected over, we'll tell you in the picture, line M. So you can ignore line N, it's just there to distract you. If A was reflected over N, think about if I drew the line that hits N at 90 degrees, it would hit over here and B would be up here. but the line that connects A to line M at 90 degrees puts B over here. And so you can see this was reflected over line M. And so for this example, we want to name B using reflection notation. So like this. We want to represent this so that we know which line this was reflected over, what was the pre-image, and now what is the image that we're looking at here. So in the figure at the right, the reflection of image of A over line M is B. That means A was reflected over M, B is now the image. So we're going to say the reflection over line M of what we started with, A, equals B. So this basically says we reflected point A over line M, and the result is B. All right, let's flip this over. All right, so let's do this on a graph now, a little more mathematical. So find the reflection image of -3, 4 over the y-axis, the x-axis, and I'm actually going to add one more on top of that. So let's first put this on the graph. -3, 4. That's your x and your y. So this is your x, and this is your y. So -3, +4 is right there. Now, if we're going to reflect this over the x-axis, the y-axis. We'll do the x in a second. The y-axis. We have to figure out how far away it is, and not just any random spot, but directly to at 90 degrees. How far away, how many units away is this point? And we're going to put it exactly the same amount on the other side. So 1, 2, 3 away from the y-axis. 1, 2, 3 away on the other side. That would be the reflection over the y-axis. If we folded this paper right on the y-axis, this point would translate right to here. So the answer here is this new coordinate, which the x is now +3 and the y is 4. So notice what that looks like. We had -3, 4, and the reflection over the y-axis is +3, 4. So when you reflect over the y-axis like this, the y value doesn't change, okay, but the x-axis, or the x value, goes from negative to positive. And if I started over here and reflected this way, it'd go the other direction. So we're going to take the opposite of the x, and we're going to keep the y the same. So let's see what happens with the x-axis. So if this is the line I'm going to reflect it over, going back to the original, directly to the x-axis, 90 degrees, 1, 2, 3, 4. It's going to go 1, 2, 3, 4 on the other side. So that point has an x value still of -3, so that hasn't changed. But my y value now was up at 4, and now it's down at -4. So when I reflect over the x-axis, the x value stays the same, and the y value becomes the opposite. Now I want to add one more here because you're going to see it in your work, and this comes up a lot. We're going to reflect it. Now we can reflect it over any lines that we want. So let's actually do a couple here. But first let's just start with x equals -4. So we need to be able to graph that line. We're going to reflect it over it. So you go to the x-axis, -4. This is the vertical line. That is always at x equals -4. If I was going to reflect over that, it ends up on the other side, the same distance. Okay, so it would end up right here. And so that new point has an x value of -5, and it still has a y value of 4. So we're going to reflect over other lines, so it's important that we remember how to graph those horizontal and vertical lines. And the last one I want to add is neither horizontal nor vertical. Y equals x. So how do I graph y equals x? Well, think about it. Whatever the y value is, the x value is the same. So if the y value is 1, the x value is 1. So 1, 1. 2 equals 2. 3 equals 3. -5 equals -5. So if I go -5, I got to go down -5. So -1, negative 1, negative 2, negative 2, positive 1, positive 1. They're equal to each other. If the x value is 2, the y value is 2. So it is the diagonal line that goes through the origin, because 0 equals 0, and it has a slope of 1. And so if I'm taking this, you can kind of count diagonal boxes here. 1, 2, 3.5. Here's your half. 1, 2, 3. Puts it right here. And let's examine that point. That's the point 4 down 3, negative 3. So from the original, how did I get here? We talked about on these ones, y value changed the same, the x became the opposite. On the x-axis, x value stays the same, y becomes the opposite. This is another special one. If you notice, the x and the y value just flip spots. 4 became the x, negative 3 became the y. So when you reflect over this special line, y equals x, it goes to the diagonal quadrant over here. And what ends up happening is your two values just flip spots. All right, so let's try one more like that. We go down to example number 2. Find the image of 5, negative 2. So x and y, this is my y, that's my x. So over to 5 for the x, negative 2 for the y. Let's start by reflecting that over the y-axis. So if we go directly to the y-axis, we are 5 away. We're going to go 5 on the other side. So that puts it right here. So when I reflect over the y-axis, the y value doesn't change. So I'm still at negative 2 for my y. I'm down 2. But now my x value becomes the opposite. So now I'm at negative 5. If I reflect over the x-axis, go directly to it, 2 away, go up 2. Here's my new one. When I reflect over the x-axis, I'm still at x equals 5. So my x value doesn't change. My y value becomes the opposite. I'm now at positive 2. And again, let's add that last one. Reflect over the line y equals x, the diagonal line through the origin. So you could try and measure it and go on the other side, but let's just use our rule here. We should just be able to flip this. And so negative 2 was the y, it becomes the x. 5 was the x, becomes the y. So negative 2, 5 puts me right there. And if I count it over diagonally, I'm the same distance away from that line. If I connected these, remember the special name, the segment that connects the image and the pre-image, this line, the reflecting line, is the perpendicular bisector. So I'm the same distance away. It's cutting the segment in half. This one equals this one, and it's hitting at 90 degrees. Perpendicular bisector.